Today we discuss about the diffusion capacitance, temperature effect and transient effects. What are these? First of all, we start with the temperature effect. Operating temperature has a profound effect on the device performance. In both the forward bias and reverse bias conditions, the magnitudes of the diffusion and the recombination generation currents depend strongly on the temperature. We consider the forward bias case. The ratio of the whole diffusion current and the recombination current is given by this equation, that is I diffusion divided by I recombination is equal to 2 Ni by Nd, Lp by W, tau r by tau p, e to the power qv by 2 kt, that is nearly equal to exponential of in brackets minus Eg minus qv by 2 kt bracket close. This ratio depends both on the temperature and semiconductor band gap. The lower figure shows the ratio dependence on both the temperature and semiconductor band gap. This figure allows the temperature dependence of the forward characteristics of the silicon diode at room temperature. For a small forward voltage, the recombination current generally dominates, whereas for a higher forward voltages, the diffusion currents dominate. At a given forward bias, as the temperature increases, the diffusion current will increase more rapidly than the recombination current. Therefore, the ideal diode equation will be followed over a wide range of forward biases as the temperature increases. The temperature dependence of the saturation current density Js for one-sided p-n junction in which the diffusion current dominates is given by Js is equal to, as shown over here, nearly equal to q dp pno divided by Lp. This is equal to Na square. This is nearly equal to exponential of minus Eg by kt. Thus, the activation energy obtained from the slope of the plot of Js versus 1 by T corresponds to the energy band gap Eg. In the reverse bias condition for a P plus N junction, the ratio of the diffusion current to the generation current is given by this equation. I diffusion divided by I generation is equal to NILP tau g divided by NdW tau p. This ratio is proportional to the intrinsic carrier density Ni. As the temperature increases, the diffusion current eventually dominates. The figure shows the effects of the temperature on the reverse characteristics of the silicon diode. As low temperatures, the generation current dominates, the reverse current varies as root Vr in accordance with the equation which we have discussed earlier. For an abrupt junction, that is W minus which is nearly equal to under root of Vr, as the temperature increases beyond 175 degrees centigrade, the current demonstrates a saturation tendency for Vr greater than or equal to 3 kt by q, at which the point the diffusion current becomes dominant. Now we discuss about the charge, storage and the transient behavior. Under the forward bias, electrons are injected from the N region into the P region and the holes are injected from the P region into the N region. Once injected across the junction, the minority carrier dominates with the majority carriers and decay exponentially with the distance, as we have shown in this equation. These minority carrier distribution leads to the current flow and the charge storage in the P-N junction. We consider the stored charge, its effect on junction capacitance and the transient behavior of the P-N junction due to sudden changes of bias. The minority carrier storage. The charge of injected minority carriers per unit area stored in the neutral N region can be found by integrating the excess holes in the neutral region shown in the shaded region in the middle of the figure which was shown earlier. So, Qp is equal to Q integral of Pn minus Pn0 dx with the limits of xn to infinity. So, this boils down to Q integral of Pn0 e to the power qv by kt minus 1 e to the power of minus x minus xn bracket close divided by Lp dx with the limits of xn to infinity. So, this equation becomes QLP Pn0 e to the power qv by kt minus 1. A similar expression can be obtained for the stored electrons in the neutral P region. The number of stored minority carriers depend on both the diffusion length and the charge density at the boundary of the depletion region. We can express the stored charge in terms of the injected current. So, we have Qp is equal to Lp square divided by dp jp xn, this is equal to tau p jp xn. This equation states that the amount of stored charge is the product of the current and the lifetime of the minority carriers. This is because the injected holes diffuse further into the N region after recombining if the lifetime is longer. Thus, more holes are stored. The diffusion capacitance. The diffusion capacitance, the depletion layer capacitance considered previously accounts for most of the junction capacitance when the junction is reverse biased. When the junction is forward biased, there is an additional significant contribution to the junction capacitance from the rearrangement of the stored charges in the neutral region. This is called the diffusion capacitance, denoted by CD, a term derived from the ideal diode case in which minority carriers move across the neutral region by diffusion. The diffusion capacitance of the stored holes in the neutral end region is obtained by applying definition CD is equal to AQ P D divided by dV. So this becomes equal to CD is equal to A Q square LP Pn0 divided by KT e to the power of QV by KT, where A is the device cross sectional area. We may add the contribution of CD to the stored electrons in the neutral P region in case of significant charge storage. For a P plus N junction, however, NP0 is very much less than Pn0 and the contribution to CD of the stored electrons becomes insignificant. Under reverse bias, that is V is negative, we show the above equation shows that CD is inconsequential because of the negligible minority carrier storage. In many applications, we prefer to represent a PN junction by an equivalent circuit in addition to the diffusion capacitance CD and the depletion capacitance Cj. We must include conductance to account for the current through the device. In an ideal diode, the conductance is obtained as G is equal to A dJ divided by dV. This is equal to QA by KT JV e to the power of QV by KT. This is equal to QA by KT J plus JS. This is nearly equal to QI by KT. Now, the diode equivalent circuit is shown in this equation, in this diagram, where Cj stands for the total depletion capacitance, that is the result of the equation times the device area. For low voltage, sinusoidal excitation of the diode is biased coincidentally at DC. The circuit shows it provides an adequate accuracy, therefore we refer to it as a diode signal equivalent circuit. Now we discuss what is the transient behavior. So for transient behavior, for switching applications, the forward to reverse bias transitions must be nearly abrupt and the transient short time. This shows a simple circuit where forward current IF flows through a PN junction. At time t equal to 0, switch S is suddenly thrown to the right and initial reverse current IR, that is nearly equal to V by R, it flows. The transient time t off is plotted in this diagram. It is the time required for the current to reach 10% of the initial reverse current IR. The transient time may be estimated as follows. Under the forward bias condition, the stored minority carriers in the N region and P plus N junction is given by the equation. QP is equal to tau P, JP is equal to tau P IF by A, where IF is the total forward current and A is the device area. If the average current flowing during the turn off period is IR average, the turn off time is the length of the time required to remove the total stored charge QP. T off is nearly equal to QPA divided by IR average, that is equal to tau P IF by IR average. So we have in this circuit the transient behavior of a PN junction, switching circuit, and the transient response of the current switched from forward bias to reverse bias we have plotted over here. And then we show the normalized transient time versus the ratio of the forward current to the reverse current in this figure. The turn of time depends on both the ratio of the forward to reverse currents and the lifetime of the minority carriers. The result of a more precise turn of time calculation accounting for the time dependent minority carrier diffusion problem is shown in this figure. For fast switching devices, we must reduce the lifetime of the minority carriers. Therefore, recombination generation centers have energy levels located near the mid band gap, such as gold and silicon, are usually introduced. Thank you.